the whole lesson. Now we move on to a new world. The world we're in today are exponential functions, which you are familiar with. We did those in pre-calc 30. Exponential function, remember those are those ones that there's either increasing or decreasing. Remember the problem we all did with the bunnies who populate very, very, very quickly. The more bunnies they are, the more bunnies there will be. That's exponential growth, okay? So we are going to be finding the derivatives of exponential functions today. Now, the exponential function you are the most familiar with is this guy right here. F of x is equal to a to the power of x. A can be any positive constant. So A is 1, 2, 3, 4, 5, all the way up, okay? So our A is our base, it's a number, but then our exponent has the x in it. Okay, so we're going to be looking at exponents today, and that's where our x's lie. So we're going to be taking the derivatives of the exponent part, essentially, today. So that's the one you're familiar with. The other one you're familiar with, we did this a couple chapters ago, is when it's e to the x, not a. E is a special number. We talked about this in chapter 1. E represents Euler's number. That's at 2.718. Okay, if you want to go back to your chapter 1 notes and review that, you can. But E is a special number. It's 2.718. So we're going to be dealing with both of those today. Okay, a to the x. A is going to be any random number, but also specifically e to the x. Now, as always, I just kind of tell you what the derivative will be, just like trig functions yesterday. Remember, right? I had those 6 for you, and I told you what the derivatives are. Same thing here. I'm going to tell you what they are. These are on your formula sheet. You don't need to memorize them, but they're actually not that hard. If I want the derivative of a random exponential function with a base of a, which will be any random number, okay, what you do is you actually recopy it. Okay, just a to the x. Don't touch it. Just recopy your power here, a to the x, and then we multiply it by the natural log. Again, this is back to chapter 1. Remember that ln a little bit? That natural log of a. So whatever that base is, we repeat it. And then we take the derivative of what the exponent was. Okay, so we recopy, we write natural log of that same base, and then we multiply it by derivative of whatever that exponent could be. And that exponent could be a monomial, a binomial, a trinomial. So you might have to use the product law within that exponent. Okay, that's how you deal with a to the x. And then e to the x, when you see an e, so specifically the 2.718, when you see an e to the x, the derivative of that, again, you just repeat it. So that's kind of a common theme here. You just repeat what I give you, and then all you have to do for e to the x is just multiply it again by the exponent of x. So they're very similar. This one is just missing the L to the N part. So the natural log part only comes in when you have an A. I know it sounds like a lot. We're going to do examples and you're going to be familiar with it. But what we're going to do first is our very first proof. We haven't done a proof yet, okay? You know, yesterday when I gave you those 6 trig functions and I just told you the derivative of sine is cos. I just told you that. You guys just like believed me. You were like, okay, sure, I'll believe her. That stuff comes from years and years and years of mathematicians doing proofs and proving it, right? That's what these mathematicians make their life work on. We are going to do our first proof. So what I'm going to do is I'm going to prove to you this one. We are going to actually go through and I'm going to actually prove to you why the derivative of ex remains ex and then just gets multiplied by its exponent. Okay? This is our first proof. And there may or may not be a proof on your test for this one. Okay? So here we go. We're going to prove that. And that's what I left the space for right here. We are going to use the limit definition. The limit definition are those equations we learned last unit. Remember last unit how I always talked about equation 1 or equation 2? You can use either of those equations to find the derivative. We're going to use one of those equations to find the derivative of ex. Okay, and I'm going to prove it to you. You guys get to take out your calculators today for the first time. You can have your calculators because we're going to use this number, okay? Some fancy calculators even have an E button on them. And when you press your E button, this number will pop up. So try to look for it. It's dust. Your calculators are dusty. Take them out, brush the dust off. See if you have an E button. You might have to press the second. Oh, you have it. There you go. Okay. Oh, you have it. What happened? Okay. If you don't have it, that's okay. Because you can just manually type in that number. No big deal. Okay. So let's prove why the derivative is what it is using the definition of a derivative. So you guys may remember from the last chapter, we defined the derivative as the function of x plus h minus the function all divided by h as h approaches 0. That is one of the equations we saw last chapter. That should look familiar. So we are going to use that definition of a derivative, plug in our stuff, and I'm going to prove to you that the derivative of ex stays ex. Okay? All right. So let's plug in. We are trying to find the derivative of this function right here. So when I rewrite this, I again have the limit as h approaches 0. And now I plug in this part, my function at x plus h. So that means that wherever we have our function, wherever there's an x in our function, our x gets replaced with the x plus h. Okay, then that's that red part I've circled. Okay, then I have to minus off my regular function unchanged. So I minus off my regular function, which we're dealing with, which is e to the x, and that's still all divided by h. Okay. So we have to do some manipulating. That's what proofs are. Proofs are manipulating things, moving stuff around to get our desired result. So what I'm going to do is I am going to take this, and we are going to use our knowledge of exponent laws, which we learned in grade 9. When you are adding two exponents together, let's look at my poster that I use with my grade 9s. Look at number 1. Something to a power of something, so a to the n times a to the m just becomes a to the m plus n. You add your exponents together. So that's a situation I have. I have something, a base with exponents added together. Let's work backwards. What did that actually mean? It actually means that I have e to the x times e to the h. We're actually going to go kind of backwards with our exponent laws. So it's e to the x times e to the h. That's what that truly means when you're adding exponents, right? And then I still have the subtraction of e to the x. And then my denominator is h. Our denominator is patiently waiting. It's going to be h all the time. Okay, we have to manipulate further. Anybody see something on the top that I can like manipulate or do or take out or I don't know? Yes. I can take out ex. I can factor out the common ex. Very good, Lily. So I'm going to factor out an ex from each term. When I factor out my ex from this first guy here, all that's left is e to the h. And then what do I have? Minus 1, right? Because I divided ex by ex. And then my denominator is patiently waiting. Okay, at this point here, there is no manipulating to be done anymore. I can't factor anything else. I don't have radicals, so I'm not going to use conjugates. I don't have a fraction in the numerator. I'm not going to use common denominators. So all those typical things we've done in the past to manipulate, we can't do anymore. So because we can't do that anymore, we are going to now start plugging in. We're actually going to start plugging in numbers because there's nothing else we can do. So here's what we're going to do. We know that h is actually approaching 0, right? The limit told us that, the definition. So wherever I see an h, I'm going to plug in with a number that is approaching 0. What numbers do we typically use if I want to approach 0? Think of that table of values I do. What's a number that approaches 0? Yeah, negative or positive, right? Either way, because it doesn't say left or right. I just say anyone. So a number super, super close to 0 is 0.0001. That sounds familiar. We've done that a million times before, right? Okay. So we are actually going to plug that in the next step. Okay, so e to the x stays because I'm plugging in where I see h's. H is approaching 0. So that e to the x, I'm not plugging in yet. Okay, then we open up our bracket. And now we're going to actually start plugging in with these guys here. E is 2.718. Okay, so we're going to actually replace that first E with 2.718 to the power of H, but we have agreed that H, we're going to use a number that approaches 0, because that's what H is doing, minus 1, close the bracket. And then now we are dividing by H again. So we are using that same H value that we chose to plug in the exponent. Did you guys want to come in? They're like lurking with the poppies. Okay, here's where you can get your calculators out because even Miss Wolf wouldn't expect you to be able to do that in your head. Right? So take out 2.718 or press your E button. You have it. Put it to the exponent of 0.001, and you can do this all in one step. So on your calculator, you typed in 2.718 to the power of 0.001. Then you minus a big fat 1 from that. You press equals. You're not done yet, because now you have to divide by the 0.001. And you should get an answer that is H. You should get an answer that is incredibly close to 1. Yeah, what did you get, Lily?
1.005000.
Right, what? And the smaller remaining ones, this, if I would have chosen 0.000000000000001, we would your answer would be even closer to 1. It'd be like 1.000000000 then the 5. Okay, but my point is, when we do all of this, we get an answer very close to 1. Did everybody try it and get an answer very close to 1? Janaea, you shook your head.
Oh, I just forgot to use my calculator.
Oh, it's been so long. Okay, so you guys believe me though that all of this, all of this comes out to being 1? Oh my gosh, Miss Wolf. You got it, Janaea? Okay. So in my next step then, I still have this EX, but now it's multiplied to that answer we just got, which was 1. And what's e to the x times 1? E to the x. So we just proved, you guys just did your first proof. You just proved that the derivative of e to the x is still e to the x. That's how you prove things. That's what mathematicians do all day long. Is do crap like that, and then they write books about it, and then they publish it. You guys just did your first proof. And there is a proof on your exam. Okay, so you're going to have to remember how to do this. Remember the process. So now that we have done our first proof, we are going to use those 2 laws above, and we are going to actually start finding the derivatives. I think these guys might be coming in. Hello.
We're back.
You're back. We have money for you.
Today we're only giving
Oh, awesome. I love that.
and tomorrow if
For sure. Here, I have a bunch of orders, you guys.
Yeah, no, let me get some. We ran out.
Oh, you ran out?
Yeah, they're short supply, so it's just, I think he's going to get some.
Okay, sounds good. Okay, so I have x squared. Okay, question for you. Is x squared an exponential function? Is x squared an exponential function? Does the exponent contain the x? No. The exponent doesn't contain the x. This is just a basic x squared polynomial that we're used to, but it's multiplied through the exponential function. So we have a product law here, right? Do I need to restate the product law?
No.
Are we good?
Yeah.
Okay, let's roll. So product law, take the derivative of your first term, which is 2x. We're good at that. And then you multiply it to the second one unchanged. And then I add, and I repeat the process, but reversed. So now I have to take the derivative of e to the x. We just proved it. The derivative of e to the x will remain e to the x, but I need to remind you that the chain law is always lurking. So you always have to take the derivative of the x, but what's the derivative of x? Am I going to write it? No. Okay, but it's there in your minds. It's there. And then I multiply that by my first guy unchanged. We are done. Cool? Not so bad. Okay. All right. Ooh, did I just combine trig with exponential functions? I did. Okay. So what's the derivative of an exponential function with e itself? It remains unchanged. So you recopy. But now the chain law is always working. So someone tell me what I do. What do I multiply it by? Nope, not quite x. What? Nope. Close. The derivative of it. That's what you're trying to say. That's what you're saying. Okay. Shh. Okay. I don't know why I'm so excited for this lesson. Okay. So the chain law is always working. You take the derivative of the exponent. So the derivative of sine, if we remember back to yesterday, is cos. Done. But remember, because we might get into this, the chain law is always lurking. So you would have to take the derivative of this guy, like we were doing yesterday, repeatedly. But what's the derivative of x? Am I going to write it? Okay. Okay. Oh boy. I have a product law. Okay. So the first thing I do is I'm going to take the derivative of e to the negative 3x. When you are taking the derivative of an e, life is good. It's almost like a freebie. You just recopy it. But now I'm still in the process of taking the derivative of this, so I've recopied it, but now the chain law is always lurking, so I have to multiply it by the derivative of that exponent, which is negative 3. Then you multiply it by your second guy unchanged, and now we repeat the process but reversed. So now I'm going to add it to the derivative of cos of 2x. Okay, so this is yesterday. You may have to go back to your yellow sheet. What's the derivative of cos? Negative sine. You recopy whatever the x is, which is 2x. The chain law is always lurking, so now I multiply that by 2. Am I done? What do I have to do? Recopy your first guy unchanged. Do we want to simplify this one together? Okay. Well, the simplification isn't that bad. Look at this guy. All you can do is toss that negative 3 in front. Like there's really only rearranging to do here. Okay, you cannot multiply the 3 and the 2. That 2 is buried inside. Okay, he can't come out. And then all I can do here is I'm going to change it to a big fat subtraction. We see the positive and the negative, right? And then I will just put that monomial of 2 in front. And then I'm going to recopy, but just remember it's a positive sign now. We took that negative out. And there we go. Okay, doke. Is it so bad yet? It is? Okay. Do we need a mental health minute? Keep on rolling? Okay. What do I have here? What law am I going to use? Do I have two things multiplied together? Okay, so what law am I going to use? Product law. Okay, so e to the x is my first function. And so I take the derivative of e to the x, which is e to the x. I remember the chain law is lurking, but the derivative of x is 1. I don't write ones. And now I recopy my second guy unchanged. Now the second half of the product law is the reverse. So I have to take the derivative of sine of x plus pi. Gross, right? We can handle it. No big deal. The derivative of sine is cos. When you do the derivative of trig functions, Hayden, you were gone yesterday, so this might be a little bit weird. When you take the derivative of trig functions, you write the new trig function cos, you recopy whatever that bracket is. Chain law is always lurking. So what is the derivative of my chain? What's the derivative of x plus pi? What? What's the derivative of x? 1. What's the derivative of pi?
0.
Why?
It's a number.
Because it's a constant. 3.4. So really, I took the derivative of x, which is 1. Am I going to write the 1? No. Shh. But then I remember that you have to multiply it by the first function unchanged. Is it okay? Okay. Don't get mad at me, Lily. I feel like there was a tone to that yes. All right. This is the first question so far where it's not an E, right? We still have an exponential function because my exponent has the x in it. That's how I know it's an exponential function. But my base isn't E anymore. This is like an A. Remember I gave you a base of A? A can be 1, 2, 3, 4, whatever. So I've given you a 2. So now we have to go back and use that other law, this one here. Okay, it's not an E to the x anymore, it's an A. So for this guy, we recopy natural log of the base and then the derivative of our exponent. All right, so let's do it. Okay, so we recopy the entire thing. So my derivative of y is recopied. I multiply it by the natural log of that same base. And then I multiply it by the derivative of my exponent, which is x squared. The derivative of x squared is done. Done. Am I going to multiply any of these 2's together? Can I? You can't, because this 2 has an exponent on him. He's like protected. He's his own being. This 2 is attached to the natural log. He's protected. And then this 2, he could multiply to someone, but he has no one to multiply with. So we leave it. Okay? Okay, poor guy. Last one like this, and then we get into the best thing ever, which is implicit differentiation. Okay? Last one. I have an exponential function again, but my base is A, not E. It's a 5. Tad, do you have a question? Or an answer for me? What, okay, tell me, what am I going to do? And then, do we agree with Tad? I agree with Tad. I think that's fantastic. Recopy, took the natural log of the same base, and then you take the derivative of your exponent, pop the 3 down, 3x squared minus 1. Okay. So actually, maybe is this a bit lighter than yesterday? A little bit? Okay. Implicit. All righty. I feel like you guys are actually quite good at implicit. You guys are good. And it's the same process every single time. We just use our new laws. Okie doke. So the first thing I see, I take the derivative of everything. We know that. So the derivative of my first guy is an E. So I know the derivative of an E is recopied. The chain rule is always lurking on the exponent. And my exponent is an x times y, which means I have to use the what? What? product law, right? So I have to multiply this by the product law. The derivative of x is 1. I'll just write everything. And then you'd multiply it by y unchanged. Added to the derivative of y is 1. What am I going to add? Dy over dx. And then don't forget to multiply it by the other guy unchanged. Okay. Now I take the derivative of 3x. I'm so happy. No dy, right? And then I take the derivative of 2y, which is 2. And then I tack on my dy dx. I just took the derivative of a y. Okie doke. What am I going to have to do on my left-hand side? Distribute. Very good, because that dy dx is protected in those brackets. We got to get them out. We're breaking them out. All right, so when I multiply that first set, I get y times e to the xy. You can have the y after. Doesn't matter, as long as you recognize they're multiplied together. And then I am going to multiply e to the xy times x dx. So I just always get in the habit of putting the variable first. You don't have to. And then I have the exy, and then I still have the dy dx. So that looks a little bit messy. Okay, and then nothing to do over here. We are good. All right, someone tell me what I do next, now that I've broken him out. Dy dx on the same side. So he's going to come over and join us. She's going to head over to the right to go away. I'm genderizing terms. I know, sorry. I'll use they next time. Okay. All right. So I have an x e x y dy dx minus 2 dy dx. We all know why it's a minus. I don't need to explain that, I don't think. Then I still have a 3 on the right minus the y e x y. Am I going too fast? Okay, next steps. Joyce, what do I do next? On my left-hand side. I sure do. Factor it out. I am left with x e to the xy minus 2. Close it up. My right side is patiently waiting. Oh, xy. I put an extra e in there. Why do I have the word I? 3? Oh my God. 3 minus y e x y. I had an extra I and y and e. Oh my God. I had an extra e in there. Holy smokes. Okay. Final step, Keith. Yeah. We divide this guy off, which essentially just means he gets slid over underneath to the other guy, right? Okie doke, final answer, dy over dx is equal to 3 minus y e to the xy, all divided by x e xy minus 2. Do I have an extra e or y in there anywhere? I don't think so. I think we got it. Okay, let's do one more. Any questions on this guy? Okay, one more. Write small. All right. Because we can see I have a product law. Okay, no product law. But this time here I see my exponent is a y. Okay, so we just have to slow down and think. All right, first guy. When you take the derivative of something with an e, you recopy it. Don't overcomplicate that. But now I have to take the derivative of the exponent, which is a product law. So my product I'm talking about is it's 2x times y, right? That's really what I'm working with. So the derivative of my first guy, 2x is 2, and then you multiply it by the y, unchanged, added 2. Now you take the derivative of y, which is 1. I'm not going to write the 1, but I know I need a dy dx now. And then don't forget that is always multiplied to the first guy, unchanged, which was 2x. Okay, added 2, same thing. Derivative of e to the 2x will be repeated, e to the 2x, but now I multiply it by the derivative of the exponent, which is just 2. That's not a product law, it's just a constant with a 2, with an x, sorry, so it just becomes 2. All right, Now, on the other side, you take the derivative of e to the y. So whenever you take the derivative of something with e, you recopy it. And now I take the derivative of my exponent. What's the derivative of y? 1. So I normally wouldn't write it, but what am I going to write? dy dx. Okie doke. So unfortunately, again, we have that distribution thing, so I have to break him out. So let's distribute. E to the 2xy times 2y, it becomes 2y times e to the 2xy. Okie doke. On to the next. When I multiply to that second guy, I don't know why I do this. I always put the 2x in front. It doesn't matter though. And then I have the e, and then I also have a dy dx. I'm just trying to tell you that it doesn't matter the order that you arrange these. Multiplication is commutative, right? It doesn't matter. You can go either way. And then I have that, oh, no, not equal sign yet. I forgot about this last guy. I have a 2e2x. I just rearrange those. You don't have to though. And then on the right side, this guy goes unchanged because it's the only term. Don't have to distribute. There we go. Alrighty. So now I have to locate my dy dx terms and get them on the same side together. So actually, that arrow, I don't like that arrow. I looked at it more closely. What should I do instead, actually? I was going to move him over here, them over here, so I got my dx's on the left, but what would actually be smarter? Yeah, just move this guy to the right so that these guys remain unchanged on the left. Okay? All right, so I'm going to remove him, and that's the only movement I have to do. So I recopy my left side, 2y e 2xy plus 2e2x equals. On the right-hand side, I have that existing ey, and I am minusing off that new guy I am bringing over, 2xy dy dx. Okay, so none of this is new. You guys are used to moving stuff around. And our final step is to factor out the right side. So I'm just going to recopy my left. And then on the right, I know I'm factoring out my dy dx. When I do that, I am left with e to the y all by itself minus 2x e to the 2xy. And your final step is always the same. You divide this guy off, which essentially means you send him over to be the denominator of your other guy. Okay, so I'm just going to do a shortcut here and just slide him down. No, instead of rewriting the whole thing, but we know that it just got crossed off. Are we okay? How did we do? Okay? Whew! So we did trig, we did exponential. Tomorrow is logs. Okay, so we're going to be in the log world tomorrow. Sorry. Thursday. Oh my gosh, a week from now we're doing our next lesson. That's wild. That reminds me, let's just go through this. Work period tomorrow. Remembrance Day liturgy, we go together. Okay, so make sure we all stick as a group, and I'll show you where we're sitting on the overhead projector tomorrow. And then no school Monday, Tuesday. On Wednesday, you will have a quiz. So your quiz Wednesday is all trig. Okay. And then finally on Thursday, we'll get to our next lesson, which is logs. So we have a bit of a break, a bit of a reprieve. All righty. So with the time remaining, which is, oh, we didn't do too bad. We still have like 28 minutes. You can work on 6, 7, 8, 9, or you can, okay, I said 6, 7, but it doesn't count because it was 6, 7, 8, 9. It's different. It's 7, oh, isn't that funny too? It's like 41 is a cool number now or something. Why? What's 41?
Just one, just 6 and 7.
It's not though.
Yes, that makes sense. That was 42. Wait. So wait, what's 6 times 7?
42,
What year are we in?
2025.
Plus 42. And
Okay.
then what year are we gonna be in?
I don't know, I'm not a math.
Do
teacher.
it,
I
do
can't
it.
do math in my head.
No, you have the words.
What is it? Okay, oh, okay, fine. Okay, do I get a calculator?
2025 plus 42.
2025 plus 42?
Yes.
Okay, oh.
And you know how you got the 42? 6 times 7.
But it's 41! No, I thought it was 41. I thought you said told me to add 41. Otherwise, 41 a funny number then.
It's just fun.
I guess I just don't get it. I just have to get it. Okay, anyways, let's lock in. Let's do some of those trig questions from yesterday, please. And then we're curious tomorrow. Hayden wasn't here yesterday. He needs to log in on yesterday too, so we're gonna be nice and quiet. Who else wasn't here yesterday? My girl's over here. Okay. Yep, sure. Okay, no. Should I put up some solutions today?
How many pages should I give myself?